Well, good morning. Today is the penultimate day of school prior to fall break, and you have been working with forces and a little bit with friction. And today we're going to work with forces on slopes. Now, we've kind of looked at the idea of forces at angles before, but I want to make sure we have this idea hammered out. And I probably brushed upon it before, but we're going to be addressing this a little bit more detail now. So let's say we've got a slope and we've got a card on this slope. Let's say this slope is frictionless. Okay? So the very first thing we do when we analyze a physics problem is always try to look at where are my forces. So in this case, I have a force of weight. And I'll indicate that with a W down here, or at least I'll try to. Let's do blue here. That's weight. And then I am going to have a normal force. Now notice that this normal force is perpendicular to the slope. It is not going, and this is a common error here, it's perpendicular to the slope here. A lot of people try to make this like that. No, that's no good. So we're going to erase that puppy. That's bad news. It's going to be this direction because it's basically how hard they press against each other. So how is it that we're going to determine that idea? So that's going to be our normal force. And if that's the case, what our normal force is responding to is basically Newton's third law of motion. For every action force, there's an equal and opposite reaction force. So here the weight is pushing down on this. And so what the normal force is trying to do is trying to offset this component of the weight that is pressing into the board. And if this angle right here is theta, then this angle right here is theta. And so my normal force ends up being mg cosine theta. And that explains how hard these two surfaces are pressing together. Now, there is a component right here that is not accounted for on the free body diagram. We don't draw this on the free body diagram. We only draw the forces that actually exist. We don't break it down into components. But there was a leg of this triangle that we just drew here that is this component. And that component is going to be the opposite angle of that. And so that would be correspond to the sine of that. And so the force that is actually contributing down the slope here is going to be, let's just mythically call that the force down the slope, is going to be mg sine of theta. Now, in the absence of friction, this force down the slope ends up becoming my net force because I have no force opposing it. But we're going to find out today that we're going to start introducing friction, and there's two types of friction. One of them is static friction, which we've introduced, and that is what I have to overcome to get something moving. And another is going to be the force of kinetic friction, is the friction once something is moving. Now, as I lift something up a slope, static friction is what prevents it from sliding down the slope, and kinetic friction is going to be what slows, it's what it retards its motion as it's trying to accelerate, because it's going to limit the net force, because my net force is going to equal that force down the slope minus my force of friction. And we'll call that force down the slope, we're going to call that mg sine theta. Okay, so we're going to introduce kind of all these ideas here as we go along. And there could be other forces as well. We could be applying force, we could be pulling, we could be pushing. There's all sorts of things. We could be applying a force at an angle, which further complicates things. But let's just kind of do some introductions. I'm going to have you mostly try some simulations today to kind of get your bearings on this. So let's kind of define an initial situation. So let's say I've got a block here. It's got a mass of 5.8 kilograms, so that's great. We know that bit of information. And it's pulled up a 25-degree incline. So let's get this here. And it's pulled up with 32 newtons of force there. We know that there's a weight component. We know that there's a normal force. And we also know that lurking in here is that there's going to be a component of this weight that's going to be trying to pull down the slope here. Now, the way I've got this written, I don't know whether this component is smaller than this or whether it's larger than this. We're going to have to math this out and figure out what we've got going on. But we should be able to identify our forces. This is going to be our applied force. Oops, I need a pen for that. That's going to be our applied force. This is going to be our normal force. And this is going to be our weight. On our free body diagram, that is all we would draw. We would not include that, even though we know it exists. As a component of the force, we're going to have to figure this out. So, let's take you down the primrose path here and show you how we solve this. First of all, let us determine what we know. We know we've got a mass, and we know that that mass is going to contribute a weight of 57 newtons. So I can say that this weight is going to be 57 newtons. That's all fine and well. Okay? But there's some other things that I can figure out here as well. I know that my normal force is mg cosine of this angle here, which we said was 25 degrees. So this normal force, when I multiply that out, is 53 newtons. Now, this bears in mind a couple things here. If this angle theta is 0, the cosine of 0 is 1, so the normal force just ends up being the weight. If this angle ends up being 90 degrees, cosine of 90 degrees is 0, so there is no normal force because there's no pressing of those two surfaces together. But notice my normal force is going to be a little bit less than my weight because I'm at this angle. Now, the component of my force acting down the slope is going to be mg sine of 25. That is this leg of this triangle here, and that's trying to pull it down the slope. That's got 25 newtons of force. Let's just kind of brush this in here. Let's say the force down the slope is 25 newtons, even though I'm not going to draw that in the free body diagram. And then my force pulling up the slope was 32 newtons, FAP. So when you look at this, guys, you can kind of tell what's going on here is that this weight right here is being offset in concert by the normal forces offsetting that component of it, and then this is contributing to that force down the slope. That is not kind of taken care of in terms of the weight. But I can tell here that the net force on this system is going to be the difference between my force going up the slope and my force going down the slope. There's going to be force going up the slope of 7 newtons. So my net force is going to be 7 newtons up the slope. Now, if I would have only applied 20 newtons here, then I would have had a net force going down the slope. I would have been trying to hold something back that's trying to slide down. Okay? But, so now we want to figure out the acceleration of the block. The acceleration of the block is simply going to be Newton's second law that's rearranged. And so substitute in what I know. I know my acceleration, 7 newtons divided by 5.8 kilograms. And as a result here, we're going to find out that, let me extend the page here, my acceleration is going to be 1.2 meters per second squared up the slope. Now, you're going to be trying some simulations today that relate to these ideas. It's also going to start introducing the idea of what happens, Jesus, there's a train wreck up here. What happens if I start introducing a force of friction in this system, okay? I've got a force of static friction that's going to be preventing me from going down the slope, but if I get an object that starts sliding down the slope in this direction, then I'm actually going to have a force of friction which is going to oppose that motion. Okay, so all these factors are at play here when we do this. Okay, so what you are going to tackle is the simulations that are available to you. You'll finish up that lab finding the coefficient, and hopefully we will see you tomorrow and we'll talk about two-body problems, I should say. Okay, other than that, if you've got a question, make sure you send me a chat or an email and I'll be more than happy to answer it. Hope you guys have a great day.